Hello everyone and welcome back to another video. Today I'm going to be talking about a subject that I am incredibly passionate about. I love math, I love proofs, I love all that sort of stuff. So call me a nerd if you want, but it's fine. I really enjoy this stuff. I got my undergrad in this and I kind of want to share that with this channel. I want to put more math on this channel. I think that's something that I enjoy quite a bit and I want to share my knowledge with the world. And for those of you who aren't super passionate about it, I'm going to try to make this as accessible as possible, though given my background, it's hard to know where everybody's at. So feel free to ask any questions in the comments and let me know if there's anything with my presentation style or anything like that that I can change to make it more accessible to people. And another motivation for the way that I think about math, I find that one of the greatest things about math and why I'm so passionate about it is I think mathematics and mathematical logic give us insight into how our minds experience truth and reality. Uh, Math and mathematical logic, which is going to be the focus of this video, seek to define and explain how we make statements, how we use and combine these statements to arrive at truth. Um, in a sense, math is a conceptual construct intended to define the governing laws of our mind's proper experience of reality, which is something that I'm very concerned about if you remember watching my Why I'm a Christian video. Um, so if you accept my view on like the idea of the transcendent God, and as I explained in that video, you can kind of understand mathematical logic as an insight into the mind of God, since it's our way of properly understanding or properly orienting our mind to the laws or the conceptual constructs governing reality in that context. So, with all of that aside, I think ultimately what math can help you do in a more practical sense is understand the way your mind works, understand the way that you can solve problems and think about and understand the way people make statements, the way people make truth claims, and overall just improve your critical thinking skills and ability to analyze evidence, analyze truth, analyze different aspects of reality, because math is the governing construct of our mind's experience of reality. So, with all of that aside, I want to begin actually introducing mathematical logic. So the one difficulty in starting introducing math and mathematics proof and stuff like that is whether you start with set theory or whether you start with logic. I'm going to make a video on each, but I think I want to start with logic because to me it seems a lot more foundational. It applies to all subjects if you want to think about philosophy, if you want to think about science. It applies to everything very clearly and cleanly. It also helps a lot with computer science and different things with the way we think. And a lot of these things aren't as limited in their scope as mathematics, trying to make claims about numbers. So I'm basing this presentation of logic and my general presentation about proof on this book called Book of Proof by Richard Hammock. I read this at one point during college before I began diving into more proof-based classes. So I find that this presentation can serve as a really good accessible introduction. I had no knowledge of proof before reading this book. So I think so the book itself defines logic as a systematic way of thinking that allows us to parse the meaning of sentences and to deduce new information from old information. So from this definition, there's two components to this. One is a better understanding of the precise meaning of the statements that you're making. So as I mentioned before, mathematics is kind of the way that we can think about the way we talk about the world, we speak about the world, the way we try to find truth statements in the world. So along with that, the other component of the definition is deriving new information from information already possessed. This is the mathematical process of induction. Once we know a couple different things, or this is the logical process of deduction. Once we know a couple things, once we know multiple statements, we can use those statements to generate new statements of truth. That's how kind of the proper way of orienting our mind to using these statements to deducing truth from them. So with all of that in mind, with that introduction out of the way, let's jump into the foundation of all of this, which are propositions. So the foundation of logic are propositions, which are statements that can be proven true or false. So they have some true or false value. To better understand what a proposition is, or what a logical statement is, we can look at non-propositions like commands. One example of a command would be like, open the window. That's not really something that you can think of as true or false. You can't say it's false that open the window. Like you can say it's true or false that the window is open or the window is closed, but a command telling someone to do something is not an example of a proposition. Another example is a question, like, what's your favorite color? There's no way to say like, oh, your question is false, your question is true. That doesn't make sense. And then another one would be an undefined statement. This one's a little bit more complicated, but one example could be x is greater than or equal to 2. Until x is defined, if we don't know what x is, if we don't know what a thing is, we can't have a true statement about it. The thing is undefined at the moment. Okay. So with all of that in mind, some examples of statements are as following. Let's jump into that. First one could be the apple is red. So if we have a red apple, then this statement is true. Otherwise, if it's like a green apple, the statement is false. I should have done the true in red, but that it is what it is. I thought of that last second. Okay. So with that in mind, another example of a statement could be the sky is red. Now looking outside right now, I can see that the sky is actually blue. So this statement would be false. We'll say that's true, we'll say that's false. And then another statement that we could do is the candle is blue. So I have a candle right on my desk right now, and we can take a look at this and see, in fact, this candle is blue. So obviously this last statement is true. And this is all like, if this seems very basic, it's because it is. But this is kind of just examples of things that we can say are true or false. We make these kinds of statements every day. Math is just making generalizations, or mathematical logic is making generalizations about statements in general. So generally, when we talk about statements in math, we're going to assign them capital letters. So we'll say proposition P or proposition Q. I think a lot of times people get confused by the fact that we're using letters, and they struggle to substitute in the actual concepts being used here, and they struggle to substitute in the idea that these are propositions. But if you think about these as just, oh, these are general letters or general propositions that I could substitute any of these things in for. I could substitute in a true statement, I could substitute in a false statement. Then you can kind of start to understand what we're doing here with these letters. And ultimately we do stuff like this all the time, where we substitute in a generalized letter or symbol for a wide swath of different things. For example, when we talk about apples, we could say the apples in this orchard are red. We're not talking about any one apple. We're using the symbol of apples to refer to all of the apples, where you could substitute in any individual apple. Now, the same thing, the same concept of forming concepts applies to the idea of propositions as well, where you have the symbol P, but you could substitute in any of these propositions here. P could refer to the apple is red, the sky is red, the candle is blue. So when we're analyzing these, we should consider the possibility of true claims or false claims. The statements that we make about P should apply to all sort of propositions. And the goal of mathematical logic is to make statements that apply to all propositions P. And in math in general is making statements about things that apply to everything within a certain set. But set theory is something we can get into later. So typically in math, statements will take the form, and this is how theorems typically work. If A, then B. And we can get into exactly what this is. This is a conditional statement. We'll get into that later in the video. But in general, what math tends to do is define a class that the statement applies to, and then the truth about that statement. So you can think of this as the class of objects that you're applying the proposition to, and then this is the truth, I guess, about that thing. So with that in mind, we can look at some examples of statements within math. So we can start, let me scroll down quick. As one example, we can think of, where's my stylus? There it is. Fermat's last theorem. And for this, we can think of, the statement of this is for all natural numbers, so for all numbers A, B, C, N in the set of natural. So basically all this is saying is the class of these four numbers, this is part A, defining if you have four numbers that are four natural numbers called A, B, C, and N. Oh, hold on. This is actually important. With N bigger than 2. So this is all part of A. We know that A to the N plus B to the N does not equal C to the N. Now what exactly this means we can get into a little bit, but to begin with, the idea here is that you're saying for all of these natural numbers, if A, B, C, and N are natural numbers, so if they belong to this class, then this is true of them. With N greater than 2, then this is true. So what exactly this means, let's go through one by one. So if N equals 1, all this is saying is A to the 1 plus B to the 1 equals C to the 1, or A plus B equals C. And this is true of so many different numbers. Remember, we can just substitute any numbers in here, and it has to be true for, it's possible to find some combination of A, B, and C where this is true. So we could say 2 plus 3 equals 5. So it's true. So you're kind of proving the statement that this statement is always false when N is 1. So, but note that we're looking at n is greater than 2. And for n is 2, you have a squared plus b squared equals c squared, which is true for any right triangle side length. So you could have like, this is just the Pythagorean theorem, 3, 4, 5. So this would be true for 3, 4, and 5. So you can't say that it's always not true for n equals to 2. But any number where n is greater than 2, so like n is 3, this is never true. Oh shoot. You scroll back down. This is never true. So that's all the proposition is saying. Or for n, and for n greater than 3 also. You can never find any combination of a, b, and c where this is true. That's what the proposition is saying. And obviously it's either true or false. There's either some example where you can find a combination of a, b, and c here, or there is no example. But proving this took a very, very long time. This is a proof that was famously difficult to prove. But it's something that is either true or false, and it's something that is a more mathematical statement than something up here, like the sky is red, apple's red, the sky is red, the candle's blue. All right, so with all of that in mind, let's move on to different types of ways to connect two propositions. These are called logical connectives. So to begin with, we're going to start with the concept of and statements. So these statements are made by combining P and Q. And these type of statements are true only if P is true and Q is true. So let's see if I have an example. So one example could be 2 is even and 3 is even. So obviously this is true, 2 is even, but 3 is even is false. So with these in mind, this overall statement that 3 is even and 2 is even, or 2 is even and 3 is even, overall the statement is false because one of the claims is false. Now, one common way of looking at or evaluating different types of statements in general is looking at the truth table. So what a truth table does is it looks at all possible combinations of truth and falsehood of the underlying propositions P and Q, and then evaluates what the combination of them is. And one way of commonly denoting and is with this symbol. So I'm going to use that symbol for the rest of the video, but I'll try to make it clear that this means and. So this refers to P and Q. So if we want to look at the truth table for this statement, I'll write down every combination of P and Q here. So since P is Q and Q is true, since P is true and Q is true, then the P and Q statement is true. Since one of the two is false in the second example here, since Q is false here, that means that P and Q is false. Now, since P is false, the combination P and Q is false. And here, since both of them are false, P and Q is false. Okay, so one thing to notice here, there's only one situation where the statement P and Q is true. It's when P is true and Q is true. That's why we use the word and here. And you make and statements every day. Just when you're talking to people in your life, we say things that include the word and all the time. So scrolling down, I don't have much more room. So another example of a logical connective statement is an or statement. Let me divide this off. And the way that we denote this is P or Q, and the common symbol used for this is the opposite, like upside down version of the and symbol. So if we wanted to evaluate the same statement, so we start with 2 is even, or, oh my gosh, I keep doing this. Why is it doing this? Or 3 is even. We know that 2 is even is true, 3 is even is false, but the combination of the two is true because at least one of them is true. It's possible in the cases where both are true. So if we said 2 is even or 4 is even, since both are true, it would still be true in this case, in the way we use or in mathematical logic. In different, in real world settings, sometimes we use or as like an either or sort of thing. But in math, if we want to specify that we're using either or, we would need to say, we would need to use a combination of different statements. So we could say like P or Q and not P and Q. But for this situation, let's write out the truth table for or. So the first situation is where both P and Q are true. So P or Q, at least one of them is true, so this is true. The other statement where P is true and Q is false, at least one of P or Q is true, namely P in the situation. So P or Q is true. Next we have where P is false and Q is true. So P or Q is true because at least one is true, Q. And finally, the last situation is where both are false. So neither one is true. So the combination P or Q is false. Okay, so another example of one of these statements is we can add the not statement down here probably. Another example of one of these statements is the not statement. So this statement basically just negates the original statement. So this one is denoted oftentimes by the squiggly line, or I'll sometimes see it denoted as this sign. For this case, I'm going to use this one. So the way that this works is we'll think of the statement 2 is even again. So obviously 2 is even is true. However, if we go towards the statement not 2 is even, then since this statement is true, this statement not 2 is even is false. And the way that the truth table for this works is pretty simple. All you do is you look at P, one statement P, and then P is either true or false, and then its negation, not P, is false if P is true, and true if P is false. So up next, we're going to go into a very common type of statement for mathematical proof, which we discussed a little bit before when I was talking about propositions. We can look at what is called a conditional statement. And this statement is defined as if P, then Q. And like before, basically all it's saying is if P is true, then Q is true, for sure. So if we know that P is the case, then we know that Q is true. So based on this, we can think of, the way this is denoted is P arrow Q. And we can say like P implies Q, or if P then Q. There's a lot of different ways of talking about this. And for an example of this statement, we can think of it's November. So Thanksgiving is this month. So with this in mind, this is an example of where, since we know that P is true, it is November right now, then we also know that Q is true, Thanksgiving is this month. And the way that this truth table is drawn can be a little bit confusing once we reach some of the further ones down there, but we'll start with the first one. If P is true and Q is true, then we know that the statement P implies Q is true because P is true, which makes Q true. So we can say this is true. But if P is true and then Q is false, we've essentially proven the statement P implies Q false because there's a statement where P is true, but Q is not true. So we can't say if P, then Q. So this is false. And the bottom two are a bit more confusing, but if P is false, we can't say anything about the statement P implies Q because we don't know anything about the fact that like if P is false, then we can't say if P then Q. I'll explain this a little bit more. So since we can't prove it false when P is false, in mathematical logic we treat both of these things as true, or we treat P implies Q as true. And for an example, let's think about the proposition if you eat that, you will get sick. So the first case, this true case, is the case where you do eat whatever thing that the person's telling you not to eat, and you do get sick. So you're proving their statement true, basically. You ate it, then you got sick. The next case is where you eat the thing, so P is true, but Q is false. So you eat the thing, and you don't get sick. In that case, you're proving their implication false. because there are cases where you eat the thing and you don't get sick. So you can't say if you eat that, you'll get sick. The next statement is you don't eat the thing and you still get sick. Well, this has nothing to do with their statement. You never proved it false in this case. So in mathematical logic, we treat it as true. Additionally, if you don't eat the thing and don't get sick, you also haven't proven their implication true, because you didn't eat the thing. So you don't know that if you eat that, you will get sick. So with that in mind, let's move to what's called a biconditional statement. Block myself off some space here again. So for a biconditional statement, it is it's the case when you would refer to this basically as P if and only if Q. And one way of writing this if and only if in math is with this symbol. But basically all this means is P is true. If P is true, then Q is true. Right, here, let me extend this a little more. If P is true, then Q is true. So like before. But also, Q is only true if P is also true. So the way we can think about this in a truth table, let's write that one out. P, Q, P. Oh yeah, and the way this is drawn is with it's like the same thing as before, but it goes both directions basically. So if this is true, we know that obviously if P is true, then Q is true. And if Q is true, then P is true. Another way of thinking about this statement actually is it's true both of these directions. These two things are logically the same. So next we also have true, false. In this case, once again, it's false because obviously every time P is true, then there's examples where Q is false, and we have that example here. But unlike the previous example, if P is false and then Q ends up being true, that's where the and only if statement comes into play, because now we have an example of the person not like in the context of if you eat this, if and only if you eat this, you will get sick. This would be an example of the person getting sick even when they didn't eat the thing. So it's a case of Q outside of the context of P. So this and only if thing doesn't apply here. So in this case, unlike the first one, unlike the conditional, it would be false. So finally, you have false, false, which ultimately, oh wait, no, this is wrong, sorry. Not gonna work for me. Here, let me use the mouse. Which ends up being true, for the same reason as before. So if we think about this, if you think you will get sick if and only if you eat the thing. So the case of the first one, P would be you eat the thing and then you get sick. So it proves the biconditional true. Then the next one would be an example of you eat the thing and you don't get sick. So it proves the idea of if you eat that if and only if you eat that, then you will get sick. That proves it false. The next one is an example of P being false and Q being true. So the idea is you don't eat the thing, but then you get sick, which proves the if and only if false, because there's an example where you get sick outside of eating the thing. So that's where the and only if comes into play. And then the final example would be both P and Q are false. So this would just be an example of you not eating the thing and you obviously not getting sick. So in this case, you wouldn't be able to prove the if and only if statement false. So we treat it as true. Okay, and then just to kind of elaborate on this a bit further, let's think about the idea of, and this is common in math, of stacking these different statements on top of each other, just so we have an example where we can think about this a little bit further. So just to kind of continue our example of eating a thing and getting sick or not getting sick, we'll start with the statement. You will get sick if and only if, I'll use the IFF here, you eat a bat, or you eat a rat. So in this case, it's saying, obviously, if you eat a bat or rat, you'll get sick. But also, the only way you'll get sick is if you eat a bat or a rat. You won't get sick in any other circumstance. So let's evaluate this proposition with the truth table. So we can view this as P, view this as Q, and then finally view this as R. So here, if we write this statement out logically, we have P if and only if Q or R. And I'll put these in parentheses just to break them up and show that they're slightly separate. So if we want to write out the truth table, we've got to look at every single combination of P, Q, and R, which I will write out very quickly. True, true, true. So all I'm doing here is just writing out all of the different combinations and just trying to follow a pattern to do that. So this will get all 8 different combinations of P, Q, and R. So for example, if we're looking at here, this is the idea that you get sick and you ate a bat and you ate a rat. So obviously in this case, this combination would be true, but let's break it down a little bit further so that we understand what exactly is going on at like the intermediate steps here. So first, let's look at the idea of, do you eat a bat or you eat a rat? That way we can kind of reduce this statement down into a biconditional like before, where all of this is just one statement. So then we can literally just go through the truth table from below, and so we can just go through that truth table from below and evaluate this more simplistically. So let's start with the question of Q or R. And when we're evaluating truth tables, this is a good approach to take, honestly, in any math problem, is break things down into simpler components so that they're easier to analyze with just different rules that you've learned. And then that can help you better understand the individual rules that you've learned and all that sort of stuff. So here we'll put, once we have that, then it's kind of broken down into two statements. And then here we can add Q or R. And then here we can add like our final statement. So is Q or R true? Obviously both of them are true. So the question is, did you eat a bat or did you eat a rat? Well, you ate both, so obviously you did one of the two. In this case, you just ate a bat, so Q is true, but you did not eat a rat. But the or statement, you ate a bat or a rat, is true. The next statement, you ate a rat, just R, but you didn't eat a bat, so you did still eat one of the two, so it's still true that you ate a bat or a rat. So for the next statement, you did not eat a bat or a rat, so both of these statements are false, so obviously this whole statement is false. And then this next part is just literally symmetric to the first part if you go through true, 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 false, false, true, false, false. So we can just write down the same things here. Okay, and then with this in mind, we want to find where it's the case that P is true if and only if Q or R. So we can look at this and compare them here. So Q or R is true and P is true. So obviously it's the case that P if and only if Q or R is true. And if you're confused about this, you can look back at the table below. So we have a similar true true statement here, another true true. And the interesting thing about biconditionals is that they are true if each side of the biconditional matches each other in its truth or falsehood value. So right here we see that Q or R is false, but P is true. So in this case, you didn't eat a vat or rat, but you got sick. So that disproves the if and only if part, because you still got sick even though you didn't eat a bat or rat. So it disproves you'll get sick only if you eat a bat or rat. So it's false. And then in this case, we have the fact that you did eat a bat or rat and you didn't get sick. So it proves wrong the if part, where if you eat a bat or rat, you will get sick. So that disproves that part. So this is false. And then same thing with the next two. And finally, there's the last case. You did not eat a bat or a rat, and you did not get sick. So it proves the if and only if true once again. So with all that in mind, you have this overall truth table, and it shows how to evaluate every single combination of these events occurring. And if you're interested in this, and if you're still confused, I would suggest trying to do this with more different examples of combinations of things. So literally, if you want to, you could just literally write out all the symbols that you want and try to go through and prove all of this true or something. Literally just go through and like write out symbols. I find that can be the easiest way to understand this type of thing. Yeah. So just think through a problem, just write out symbols if you're confused about this still, and work through. And if you ever need help or are confused, just ask a question in the YouTube chat if you have any questions, and I'm happy to answer. Or if you want to kind of work through this on your own, using some of these truth tables from below to help you combine different statements, and also using the method of breaking things down into these individual components can be helpful. So for this one, you could like look at that component and then that component and then combine them, look at that component, and then ultimately combine everything into one. So, okay, with all of that in mind, with all of these somewhat complicated different symbols and statements and all of this together, let's move on to the concept of logical equivalence. So in the concept of logical equivalence, the basic idea behind it is if two statements produce the same truth table, then we know that they are logically equivalent. So for an example of this, let's just look at two statements that are logically equivalent. P if and only if Q, and that's equivalent to P and Q, or not P and not Q. And before we go into this, let's think about this intuitively. P if and only if Q. Before this was basically the rule that we talked about, where if P and Q are true or P and Q are false together, then P if and only if Q is true. So that's the way that you can kind of break this down, because you can see that first part in the statement is P and Q. So for that to be true, both P and Q would have to be true. And then for this one to be true, not P and not Q, both of them would have to be false, because if P is false, then not P is true. And if Q is false, then not Q is true. So that would be true only if these are both false. This is true only if both these are true. And this or statement means if one of these is true, then the entire thing is true. So then this entire statement is true if both P and Q are true, or both P and Q are false, which is exactly the rule that we kind of looked at before when we were looking at biconditionals, like P if and only if Q. But to understand kind of how you would want to break this down, let's go through and look at all the combinations of P and Q and see if this actually is true for everything. So to break this down, let's first start with looking at not P and not Q, and then using those together, and then we can look at P and Q. And then combining those together, we can look at not P and not Q. And then we can look at this overall statement of P and Q, or not P and not Q. And then finally, once we have that statement, we can compare it to P. And I'm running out of space here a little bit, but that's fine because we're almost done. Oh my gosh, this is gross. Okay, we're fine. Now this is why I use graphing notebooks for stuff like this. Okay, so apologies for the awful handwriting, especially near the end, but I think this should do. So let's just go first looking at P, comparing it to not P. Since this not symbol simply negates the P, we can say this is false when it's true and true when it's false. So we can fill that out here. And then since the negation of Q says that it is false when Q is true and true when Q is false, we can go through here. False, true, false, true. Now if you remember the and symbol from before, this is all only true if P is true and Q is true. So this first case it's true. The second case it's false because Q is false. This third case it's false because P is false. And this last case, since both are false, all of it's false. And the not P and not Q, we need to find a case where not P is true and not Q is true. So here we have false because they're both false. Here, since not P is false, this is false. Here, since not Q is false, then this is false. And then finally, since both not P and not Q are true, then this is true. So this is a OR statement that combines this statement with this statement. Here, let's color this so we understand. This statement combined with this statement. So here what we have is P and Q is true, but not P and not Q is false. But since it's an OR statement combining them together, this is true. In this case, both are false, so this has to be false. In this case, again, both are false, so this has to be false. And in this case, the green not P and not Q is true, so this is true. And if we remember before, from our biconditional, we remember that since both of these are true, P if and only if Q is true, since one of them is false and the other is true, these two statements are false. And then finally, since both are false, this is true. And if we go through line by line, we can see that matches, that matches, that matches, and that matches. So we know that these two statements are logically equivalent. So if you want to practice this a little bit, one thing that I could recommend is looking at De Morgan's laws. These are pretty famous laws of logic that are logically equivalent, and they kind of show how to, as we'll get into very soon, how to negate an and statement and how to negate an or statement. So not P and Q is the same as not P or not Q. And on the other hand, not P or Q is the same as not P and not Q. So what you'll see is for negating both of these, it flips this or into an and in this case it flips the and into an or. And I'd recommend that you guys go through these, the truth tables for these on your own and verify them for yourself if you want to continue practicing this. Next, what we'll get into is the concept of negation, which De Morgan's law provides a good example of. De Morgan's law is an example of negating an and statement, and here it's negating an or statement. Another thing that you can do is negate a conditional. Oh my gosh. So in this case, negating a conditional is the same as saying P and not Q. And this is something else that you can go and verify for yourself. And then to show how to negate a more complicated statement, we can talk about negating a biconditional. So to look at this, let's start here. Now, remember from before that a biconditional is the same as saying P implies Q and Q implies P, or yeah. Here, I'll add the and in there very tinily. So what you can write this out more, you can expand this to be which, if we apply De Morgan's law here, when we distribute this negation to each of the terms, this is the same as not P implies Q, or not Q implies P. And then finally, when we get to the end here, we can say, using this negation statement from before, we can say P and not Q, or Q and not P. So if we think about this, what negation ultimately does is change all of the true values in this truth table to false values, and all the false values to true values. It says when this statement is false, then the negation is true, basically. So how do we negate a biconditional? If we look at before, we would need to show that either Q is false while P is true, or P is false while Q is true. Now if we look here, this is exactly what this statement means in the English language. P and not Q, so Q is false and P is true, or Q and not P, so P is false and Q is true. And that is what makes the biconditional false. And the similar logic applies to the conditional. The only way to disprove a conditional is to show that what is being implied, the Q, is not true and the P is true. So if we look here, remember, the only way to show a conditional is false is saying this Q is false, but the P is true. Okay, so with all of this in mind, let me give myself a little bit more space. Ultimately, why this matters is because in math, we can use these statements to produce logical inference. And one second. So with these statements, what we can do is go through and look at logical inference. And looking at logical inference, we can kind of view this as like the first hint at mathematical proof here. And logical inference is when we use two statements that are true to infer or imply the truth of a third statement. So in logic, one way to do this is through what is called modus ponens. And this is like sort of a hint at the direct approach to proof. The direct approach to proof. So if we know that P implies Q and P is true, then we can deduce that Q is true. So one example of this would be if it rains, then the ground will be wet. So P is it rains and Q is the ground is wet. So if we know that it rains, then we know that the ground is wet. That's the way that you can deduce this. So you know that if it rains, then the ground is wet is true. You know that it rains is true. So combining these together, we can understand, or we can basically prove that the ground will be wet. So this is how you combine different true statements using logic into another true statement. One thing to note here is that the converse is not true. If you know that P implies Q, or if it rains then the ground is wet, and you know that the ground is wet, that doesn't necessarily mean it rains, because the reverse, you don't have the biconditional there. So the next one is modus tollens, and this is kind of a hint at the contrapositive approach to proof, but that's for a different video as well. So P implies Q, and you know not Q. So let's think about the same example. If it rains, then the ground will be wet. Well, you know the ground is not wet. What does that mean? Well, based on that, you know that it did not rain. Because if you know that if it rains, the ground is wet, you can look outside and be like, well, let's check if the ground's wet to see if it rains. Well, if you see the ground is not wet, then you can tell that it didn't rain. Note that if the ground is wet, you don't know if it rained or not, because the ground could be wet for all sorts of reasons, like before, what we talked about. So the reverse isn't necessarily true. If it didn't rain, that doesn't mean the ground isn't necessarily wet, so you can't go this direction to show not P implies not Q, but you can say not Q implies P if you know P implies Q. And then finally, let's talk about the last concept here, which is elimination. So in this case, we have P or Q, and we also know not P. So if we know that P is true or Q is true, and we know that P is not true, let's think about this actually. Let's think about this with an example from the last presidency, or the presidential election. So we either know that Kamala Harris will be president or Donald Trump will be president. Well, we know that Kamala will not be president, so not P. What does that mean? What can you deduce from this if you know that either Kamala will be president or Trump will be president, and we know Kamala is not going to be president? What do you know about whether Donald Trump is president or not? You know that Donald Trump will be president. I don't know if that's like too obvious of a way of putting it, but it's this. I mean, this type of logic feels rather intuitive, because if you know either Kamala will be president or Trump will be president, and you know Kamala will not be president, well, then you can know with 100% certainty that Donald Trump will be president. So yeah, with all of that in mind, those are three common approaches to logical reasoning and to deducing propositions based on all of these subjects that we've looked at, these subjects we've been looking at. Yeah. So with all of that in mind, this was probably a lot. I've tried to get through it relatively quickly. I still took an hour. So please let me know if you have any questions, or if you have anything that I should improve in my presentation style, or how I'm presenting these ideas in future videos, and what I can do better. I tried to include lots of examples here, or I tried to include examples for everything, and I tried to explain this as simply as I possibly could, but I know there will probably be some confusions, and there's places where I thought I explained myself well that I probably didn't. So please give me any feedback that you may have, and I'd like to implement that in future videos. So yeah, thank you all for watching, and I hope to see you all in the next video. Peace.